Hey, all right, welcome. Looks like we've got another question here, and my first one from chapter 17 on sound waves. So, as I mentioned in the video lecture, and I'll just say it now as we get started, take all this discussion we had about waves in chapter 16, and now we're going to apply it specifically to sound waves. So, number 34 says this. It says a block with a speaker bolted to it is connected to a spring having a spring constant of 20 newtons per meter as shown in the diagram. So the diagram looks something like this, if I can draw it. Here's kind of a solid wall, and then we've got this spring, and then here's this block. Looks like they mounted the speaker up here on top, and it's producing the sound waves. But the idea here is that this block then is going to oscillate back and forth. So I would say part of this problem is actually a review of chapter 15 where we did the oscillations. But let me read on here. It says the total mass of the block and the speaker is 5 kilograms. So let me just put 5 kilograms here. And the amplitude of this motion is a half a meter. And so I'm going to put A equals a half a meter. All right, so that's our given information. Here's the first question, A, page 1. Okay, so A says the speaker emits sound waves at a frequency of 440 hertz. Determine the highest and the lowest frequency heard by the person to the right of the speaker. So they have a person kind of standing over here to the right. And the crutch of the problem really is to kind of understand then that the listener here, well, I should use the word observer, that's kind of how we focused on, but the observer is going to hear the sound waves, and there's going to be some motion relative between the observer and the sound wave. Now, in this case, the sound wave, the source of the sound wave is moving, not the observer. But the point is, that was our whole idea of the Doppler effect, that the Doppler effect is this kind of this perceived a frequency. And so the little formula we derived in the lecture is this. And we called it F prime. So this is the perceived frequency that the observer would hear. It is the original frequency. So that's going to be our 440 hertz. So let me just put F. Here's the 440 hertz. This is what you might call the real frequency. This is the frequency that the paper diaphragm and the speaker is going back and forth at. But then it's going to be modified, and it's modified according to this equation, V being the speed of the waves themselves. And then there is a velocity of the observer and the velocity of the source. And I'm going to put absolute values here. And then if they are moving towards each other, they go higher. So that means if the observer is moving towards the source, there should be a plus sign. If the source is moving towards the observer, there should be a minus sign in the denominator. Each of these would make it at a higher frequency. So I kind of like to write my equation this way. And I put, okay, I use the upper sign if they're moving towards each other. Okay, the same is true in the opposite direction. So if the observer was moving away, less than 44 hertz would get to the observer, even though the paper diaphragm in the speaker is still going back and forth at 440 times a second. It's just the observer moves away. In fact, you can even see if the observer moved away at the same speed as the waves, none of the crests would actually catch them, and so you get a zero in the numerator, and you'd get a zero frequency as perceived by the observer. And then, of course, in the denominator would be a plus sign to make the denominator bigger, which makes the overall frequency smaller as the source moves away. So I wanted to pause for a moment and just kind of run through my own brain, and also just to kind of highlight to you, this is, I think, what makes the Doppler effect kind of complicated, is keeping track of these three different velocities. So we've got the v with no other symbol on it, so that's the velocity of the waves. We got the velocity of the observer, that's in the numerator. Then we got the velocity of the sources. And then we got this plus and this minus. And then maybe I should put over here away. So I'd use the lower sign if they were moving away from each other. All right, so in this case, this problem does not have the observer moving. So I could scratch that one out. That's going to be 0. And as I fill this in, this would be 440. They don't say anything about the waves. And so the default is, look, if they don't really specify, assume that these are sound waves in air at room temperature. So we know that that is about 344 meters per second then for the velocity of the sound waves. And then, of course, in the denominator, same thing. It's 344, and it would be minus or plus. We'll talk about that in a second. But it's then the velocity of our source. Now, our source, then, is what takes us back to chapter 15. Our source is oscillating back and forth. And so it goes faster, slower, faster, slower. And we learned in 15 that when it goes through equilibrium, it's going the fastest. So it would go out, stop, come back, right to equilibrium, go the fastest, come all the way out, stop. And so as it's going through equilibrium, it would be going its fastest. And that's the biggest change in frequency. And so that's really what we want here. We don't need to know all the different velocities of this oscillating object, because they want to know the highest and the lowest. So the highest frequency we're going to hear is when it's moving towards the observer, and we would use a minus sign, and we would use the biggest number there, which is when it's through equilibrium. So indirectly, they're really asking you for the maximum speed, and maybe I'll put a little sub s, because it would be the maximum speed of the source. And, of course, let me come back to chapter 15, where we had this omega A as the little formula for what is the maximum speed, or what is the speed as it goes through equilibrium. And so the omega is K over M, and then times A. And these numbers were all given, right? They gave the spring constant. Looks like I didn't write it down. Let me just put it in there now. And so the spring constant is 20. The mass is 0.5, and the amplitude is 0.5. And so if I put all these numbers together and grab my calculator, let's see, what was it? It was, so 20 divided by 0.5 is a 40. The square roots of 40 is about a 6.32, it looks like. Multiply that by an amplitude of 0.5. And so we're looking at a speed of about 3.16 meters per second. So the two different frequencies would be this. The real frequency is the 440, or the frequency that the speaker's actually operating at. And then in the numerator, I would just have this 344. And in the denominator, I'd have 344. And then when it's moving towards the observer, the fastest towards it, I would use a minus 3.16. And right next to it, or below it, I'll say when it's moving away, it would be a plus. And so I'll have an F prime when it's moving toward the observer, and I will have here an F prime when it is moving away. All right, so grabbing my calculator here, and maybe in the numerator I'll put 344. Then I'll divide by, and I'll just put in parentheses, a 344, and I'll do the minus first, minus 3.16, and close parentheses, so that'd be that factor. Then as long as I'm here, I might as well say times 440, and this comes out to be a frequency of 444 4 hertz. So we're going to hear just a little bit higher by about 4 hertz. Now, it's not a linear function, but it's such a small change that it's probably then going to be a decrease of 4 hertz when you move away. And so let me just go back to my enter and re-edit and come back here, and instead of having a minus sign, I'll put a plus sign, and let me just check these numbers. So 344 divided by 344 plus 3.16, and then times 440 and 336. So 336. So yeah, it went down by roughly 4. Again, not really a linear function, but it's so a small spread that even a curved function looks straight for a little ways. But that's the idea. That's the Doppler effect here. So hopefully that makes sense here. Now, let me go to the next page here and go to B. And so B is saying, if the maximum sound level heard by the person is 60 decibels, what is the intensity? All right, so this idea of sound level measured in dBs, decibels, is 10 times the log of the intensity divided by some reference point. And so whether it is greater or smaller than the reference point. And for sound waves, the reference point is an intensity of 10 to the minus 12 watts per square meter. And so they're saying it is a decibel reading of 60. So if I move the 10 to this side, I get a 6, and I'll just go log of that stuff. And then I'll take the anti-log, because that would be then a million, so 10 to the 6th, natural, once we get rid of the natural log, and then this will be 10 to the minus 12. And then if I bring this to the other side, that's 10 to the minus 6. And maybe I should put units. So it would be 10 to the minus 6 watts per square meter for the intensity that the person is hearing. All right. Hope that helps.